Hi, I'm Chem's best friend. I make chemistry easy. I'm a graduate of MIT, and I have more than 17 years of experience teaching AP chemistry and chemistry classes. Please like and subscribe to my channel. And if you are interested in private tutoring lessons, the information is on the screen. Hi, are you ready to learn about solutions? I am. In this video, we will be learning qualitatively about solutions. What does that mean? I'm not going to crunch numbers. We will get a nice solid foundation so you can understand solutions better. Are you ready? Let's go to my screen. What is a solution? A solution is a homogeneous mixture in which the solute is uniformly distributed within the solvent. Can you think of a perfect example? I think a perfect example would be, let's take some salt, sprinkle it in water. The salt will nicely dissolve. So the salt is the solute. So here is, let's say, our sodium chloride. And the solvent is the water. And that's a nice solution, homogeneous mixture, uniformly distributed. Here is another nice example. This is just different food coloring in different beakers. So the food coloring molecules are swimming nicely between water molecules, between the solvent. So let's just write some examples. So one of them that we just have right here is salt in water. Or an ocean. Maybe you live next to an Atlantic Ocean, Pacific Ocean, Indian Ocean. There you go. A lot of people live near the coast. Another example of a solution is iced tea. You have tea molecules, sugar, also swimming nicely distributed between water molecules. Most people think of solutions as being in a liquid state. And that is true. That's what we think. But solutions can also be in solid state or a gas state. So a perfect example of a solution that's a solid will be stainless steel. Stainless steel, or maybe you play a brass instrument. Brass is also an example of a solution. It's a uniform mixture, homogeneous mixture. An example of a solution in a gas state is the air we breathe. It's a nice mixture of nitrogen, oxygen, and some other little trace amounts of other gases. So now that we know, let's talk a little bit more about solutions. What affects the rate of solute dissolving in the solvent? What affects the rate of dissolving? Well, one of the things is temperature. The hotter it is, the faster it will dissolve. You probably have this from your experience. If you put sugar in hot water versus cold water, sugar in hot water will dissolve much faster. Another example is agitation. That means, do you stir? Again, going back to our iced tea example, if you stir the sugar, it will dissolve much faster than if you don't. And surface area. Let's go back to our iced tea. If you put sugar cubes versus powdered sugar will dissolve much faster because it has way more surface area than sugar cubes. You will need to stir more if you put sugar cubes. So what affects solubility? The amount of solute that will dissolve in a solvent. One of the things is temperature. So we will talk about that. Nature of solute and solvent, like dissolves like. Pressure has an effect for gases only. And how can we describe solutions? Well, we can use these words. We can say the solution is saturated. That is, it's full. Full of what? Full of the amount it can hold. You can say it's unsaturated. That means you can add more solute into it. Or supersaturated. It means it holds way more than it should. And what terms are used to describe relative amounts of solute and solvent? Remember, we're not doing numbers yet. And I think the best words will be something is dilute or concentrated. Here's a perfect picture. If you put a little bit of salt into a beaker of water, we say that solution is pretty dilute. Not much salt ions are going to swim. However, if you put a lot, that solution will be concentrated. So what I would like to do is talk right here what affects solubility, and then we will talk nicely, we move down this slide, example by example. So let's remind ourselves about process of dissolving. So what does dissolve mean? Dissolve means swim between water molecules. So ionic substances, in order to dissolve, in order to swim between water molecules, will break apart into ions. And then the ions will swim between water molecules. Molecular substances, some of them, will stay intact, but they can swim between water molecules. And here is a better picture of ionic substance breaking apart, splitting apart, dissociating, and swimming between water molecules. Well, the big thing that affects with something will dissolve is the nature of solute and solvent. And an easy way to remember it is that it's like dissolves like. So in the first picture, we have water, and we're putting sugar into water. Let's have a look a little bit more closely. Water is a polar solvent. Polar means it's slightly charged on one side. Glucose can form lots of hydrogen bonds. So this looks like a little bit of a water molecule, part of water molecule. So glucose can dissolve in water because it's also polar. So polar solute will dissolve in polar solvent. Here is oleic acid. And this is lots of big long chain of carbon and hydrogen, a long hydrocarbon chain, and that means it's non-polar. You can also say it's hydrophobic. It doesn't like water. So if you put oil and water, does it dissolve? No, it doesn't. It looks like this. You have an oil layer on top, then water on the bottom. It does not form a solution. So it's important that like dissolves like, sugar and water mix, but oil and water doesn't mix. Another thing that affects formation of solution is temperature. So let's look at the effect of temperature if we put a solid in the water. This graph is used in lots and lots of chemistry textbooks, and you should know how to read it and understand it. So let's look on our y-axis. Our y-axis is solubility, so grams of salt in 100 grams of water. It's important they say 100 grams of water. And our x-axis is temperature. There is a definite trend here, the effects of temperature on a solid. And you can see that all of them except one, as the temperature increases, solubility increases. You can clearly see it. So let's talk a little bit more about this green line, potassium nitrate. I really like to use that example. So what happens if I put 20 grams, let's do it here, it's at room temperature, 20 grams of potassium nitrate at room temperature water. Well, my solution is under the green line, and I'm going to call it unsaturated. I can put a little bit more. So what happens if I put 40 grams? What happens then? When I'm going to be moving up, and as I'm moving up, I'm crossing this green line. And the green line tells me when solution becomes full, when solution becomes saturated. And then no more crystals can dissolve. So what I'm going to see is my solution will be saturated, but I'm going to have 10 grams of crystals on the bottom. And no matter how much I stir or how long I stir, they will not dissolve. It will look like this. You will have these crystals on the bottom of a solution. So remember, Anything that's under the line, it's unsaturated. It means you can add more. Anything on the line is saturated, but you will not know it because you will not have a visual clue that there are crystals that can now stay and not dissolve. So if you have a solution that has crystals on the bottom, that's when you above the line, do not say supersaturated. It's rare and it's unstable. You will see crystals, so your solution is saturated, and then you will have leftover crystals. So how do you make a supersaturated solution? Well, what if we increase the temperature? So we have 40 grams of potassium nitrate at room temperature water, 20 degrees. And now we're going to start increasing the temperature of my solution. So I'm going to see the crystals disappearing. And then right here at about 27 degrees, all the crystals will be gone. And then if I raise the temperature more, the crystals will be gone, and I'm just going to have warmer solution. And now let's cool it down really, really slowly. So if I cool it down really, really slowly and carefully, and I cross 27 degrees and I get it colder and colder, let's say I go back to room temperature and no crystals formed. That means I am above the line, but I do not see crystals. That's when I have supersaturated solution. It's rare and it's unstable. Okay, let's keep going. So what effect does temperature have on gas molecules swimming? So remember, gas can actually be also a solute swimming in water. Like there's O2 swimming in a pond, so fish can breathe. And you can see that the trend is actually opposite that the temperature has on a solid. That the hotter it gets, the solubility decreases. So as temperature increases, solubility decreases. It's really interesting. Think of it as water molecules moving faster, and the gas molecules swimming between them can get out and can go up to less density, go up to the top and escape. So this has really nice and really interesting implications. Let's look at oxygen. Solubility decreases as temperature increases. Let's think of fish in the winter. Fish in the winter have way more oxygen available to breathe. They are much more happy. Fish in the summer, if you have a heat wave, the lake temperature gets pretty hot. Fish are pretty struggling. Sometimes you might even get a fish kill after a heat wave of a few days. The water temperature gets too hot, there's too little dissolved oxygen, and fish in a way can drown. Nature usually compensates by growing green plants that, again, by photosynthesis produce oxygen, but we don't need to, it's too much for this lecture. So, quickly, effect of temperature on gas. As temperature increases, solubility of gas decreases. What is the effect of pressure on solution? Well, this only will work for gases only. And let's look at this picture. Let's look at picture A and B. So here is my solvent, water, and here is some gas. Let's say it's nitrogen gas. So I have some nitrogen gas, and this gas will also, it will just escape, also evaporates. So I have some gas above. If I increase the pressure, I'm going to push these molecules closer together. There will be more collisions. And just by pure statistics, more of them will also go down. If they go down, they will go into my solution. So as pressure increases, I can then put more gas into the solution. And this is how they pack carbon dioxide gas into soda. They package them under pretty high pressure conditions, and then lots of carbon dioxide gas can go in. Okay, so if we have soda and we open it up and we want to keep it bubbly till next day because we didn't drink it all, what do? Well, one of the things we do, we can put it in the refrigerator. If you put your soda bottle in the refrigerator, it will be, you will keep the carbon dioxide, it will be it will be just another gas. Again, you will keep more gas dissolved. Or you can buy this fizz keeper. You can go to the store and buy the fizz keeper and keep pumping it. The question is, does this work? Let's think. If you put it on a soda bottle and you keep pumping, what gas are you pumping? Well, you're pumping air, and air is 80% nitrogen, 20% oxygen. You are pumping mostly nitrogen gas. But what gas do we want to keep in the soda? Is it nitrogen gas? No, it's not. It's carbon dioxide gas we want to keep in the soda. So do not buy fizz keepers. They do not work because remember here, look at the spheres. They are both the same color, purple. So you need to pump the same gas. You need to increase the pressure above the solution of a gas you want to push into the solution. You would need to increase the pressure of CO2 gas in order to push it in. But we don't have it that much in your room, in the room you're sitting in. Not enough to do it by hand. So there you go. I just saved you $5. Do not buy fizz keepers. They don't work. Okay, let's quickly just talk about concentration units that we use for solutions. One of the units we use is percent by mass. And that's you put your mass of your solute over total mass of solution, not mass of your solvent. It's the total mass of your solution multiplied by 100. That's your percent by mass. And we also use very important molarity. That's like chemists' unit for solutions. So we're going to say moles of solute over liters of solution is big M. So I call it moles over liters, moles over volume. It's my molarity. So in the next video, we are actually going to use this, especially molarity, and crunch some numbers and learn how to do calculations. But for this one, I think we got a nice foundation of what is a solution, what effects temperature have on different types of solution on a solid solute or gas solute. So I hope you learned something new, and see you next time when we will be crunching numbers.